All right, let's go ahead and get started. I want to welcome you back to Unit 11. This is Solutions, and we're talking about solubility and dilution, right? So if we have a concentrated solution and we want to dilute it, we want to know what the relationship is between the concentrated solution and the dilute solution, and here it is. It's M1V1 is equal to M2V2. In other words, the molarity or concentration of the more concentrated solution times its volume is equal to the molarity of the more dilute solution times its volume, okay? So you can make a more dilute solution or have a lower molarity from a more concentrated solution, but you can't go the other way around. Okay, so if I have a concentrated, say, mop water solution, I want to mop the kitchen floor. I can make a more dilute solution by simply adding water, but I can't make a more concentrated solution from a more dilute solution. All right, so M1V1 is equal to M2V2. So what I want to do now is I want to try a problem, a specific problem using this formula. So here we go. By the addition of distilled water, 30.0 milliliters of a 6.0 molar sulfuric acid solution is diluted to 150 milliliters. You went from 30 to 150 milliliters. What is the molarity of the H2SO4 solution after the dilution? What's the molarity after the dilution? Well, certainly we would expect a lower molarity since we are making it more dilute. So we're going to expect a number in our calculation to be less than 6.0. So here we go. We're going to use our formula. M1V1 is equal to M2V2. Now the molarity of the more concentrated solution was 30.0 and its volume was 6.0 liters. And that's equal to M2, that's the molarity we're looking for, times 150 milliliters this time. And by the way, I want you to notice that you don't have to change milliliters to liters as long as you recognize that both of these sides have to be the same. In other words, if one volume is in liters, the other one has to be in liters. If the other one's if one's in milliliters, then the other one has to be in milliliters, and you're good. All right, so let's solve for M2 by simply dividing both sides by 150.0, and when I do that, it's going to give me M2. So the molarity of the H2SO4 after the dilution, and you check me on this, check with your calculator, is 1.2. Notice two significant digits in the 6.0, 3 here, 4 here. I can only take the least of those, and it's going to be two significant digits. So this is my answer. And just as I predicted, the molarity of the more dilute solution is going to be less than what we started with, of course, which was the 6.0. It turns out that it's 1.2 molar. Okay? So that's it. Example 2. Let's take a look at this one. It says, what volume of 1.23 molar hydrochloric acid would you have to use to prepare 2.0 liters of a 0.334 molar hydrochloric acid solution? Okay? So what we're going to need to do is we're going to take this concentrated solution, 1.23 molar solution, and we're going to make a more dilute solution. The new solution is going to be only 0.0334 molar. But there's going to be 2 liters of it, right? So we're going to use our formula. M1V1 is equal to M2V2. So what's the molarity of the more concentrated solution? Well, again, it's 1.23 molar. And the question is, what's the volume that we would need to use? So that's V1. That's equal to 0.334 times 2.0. And we're going to solve for V1. So when I solve for V1, I get 0.0334 times 2.0 divided by 1.23, and I get this volume right here. So this is the volume that I would use. So if I want to take that volume up to 2 liters, what I would do is do this. I'm going to take this volume of the 0.054 liters. The more concentrated solution has that volume. So to properly dilute it, I'm going to add the difference between 2.0 and that number, which is 1.946 liters or 1,946 milliliters of pure distilled deionized water. So let's get this straight. I'm going to take this volume, 0.054 liters, and I'm going to have to increase it to 2 liters. So I'm going to have to add pure water. When I do, I get the more dilute solution. How much water do I need to add? I need distilled water, deionized water. I need to add the difference between the 2 liters that I want and the 0.054 liters of the concentrated solution. So I need to add 1.946 liters or 1,946 milliliters of distilled water to my more concentrated solution. Okay? I hope that makes sense. All right, I want to talk now about something called colligative properties. Colligative properties. What do we mean by colligative properties? Well, colligative properties are properties that change when I add something to a pure substance. Okay? So when pure solvents such as water have a solute such as salt added to them, certain properties known as colligative properties change. All right? Certain properties known as colligative properties change. Freezing point and boiling points of solvents are colligative properties. These are going to change when you add a solute to this solvent. The freezing point and the boiling point are going to change when you add a solute to a solvent. So let's take an example. For example, when you add more solute to solvent, the freezing point of water decreases below 0 degrees Celsius. So when you've heard that the freezing point of water is 0 degrees Celsius, that's for pure water. And the boiling point increases above 100 degrees. 100 degrees is for pure water. But when you increase the solute, or when you add solute to water, it's no longer 0 and 100 degrees respectively for the freezing point and the boiling point. Instead, it's something below 0 and something above 100 for the boiling point. Now, antifreeze. Antifreeze is used in cars to prevent them from overheating in the summer and freezing in the winter. In other words, if you just had pure water running through the radiator, then every time the temperature got below 0 degrees Celsius, your engine would stop working because of the fact that there's not water circulating through the engine. It's just a block of ice in the radiator, right? On the other hand, if it gets above 100 degrees, ordinarily, if you just had pure water in there, it would start boiling. You'd have a problem then too, right? But if you add antifreeze to the water, antifreeze is going to lower the freezing point and raise the boiling point so that you can drive in extreme conditions, all right? Okay, so let's take a look at the following notes. Okay, these are for pre-AP students. Okay, so if you're a regular student, you might want to kind of take a break here, although anybody's welcome to listen to these, but these are intended for pre-AP students. All right, I want to talk a little bit about aqueous solutions. What do we mean by aqueous solutions? Well, solutions in which water is the solvent is known as aqueous solutions, right? So we're going to use this symbol, AQ. There usually will be parentheses around it just like that. Okay, so if I put salt in water and dissolve the salt in water, that's an aqueous solution. The salt is dissolved in water. Okay, ionic substances dissociate or break apart completely into ions when dissolved in water. Now let's keep that in mind. Ionic substances are going to fall apart in water. So if I had, for example, NaCl in water, what's going to happen is I'm going to put an arrow just like this. I'm going to put the H2O right here because I'm not concerned about the water. I'm concerned about what the NaCl is going to dissociate into. It's going to dissociate into Na plus and Cl minus. In other words, ions. Okay? Now, some molecular compounds such as HCl also break apart into ions and are dissociated in water in a process called ionization. So this process of formation of ions is called ionization. Well, that would make sense, right? And their solutions conduct electricity very well. And these compounds are called electrolytes, okay? Electrolytes. Other compounds dissociate or ionize only slightly when dissolved in water. They conduct electricity, but not very well. And these compounds are called weak electrolytes. Weak electrolytes. The rest of the soluble compounds form absolutely no ions when dissolved in water and do not conduct electricity. And their solutions are called non-electrolytes. So strictly covalent compounds, okay, are not going to dissociate in water. They're called non-electrolytes. They're called non-electrolytes. Now let's get back to strong electrolytes. What do we mean by a strong electrolyte? Well, these include ionic compounds. Sodium chloride, potassium bromide, magnesium nitrate. All those are soluble in water, and they are strong electrolytes. Also, hydrochloric acid, hydrobromic acid, hydroiodic acid, completely dissolve in water, and they are strong electrolytes, okay? So a typical reaction would be this. If I put hydrochloric acid in water, I would get H3O plus and Cl minus. H3O plus because the H plus that dissociates is going to associate with water to form the hydronium ion, H3O plus, that's called a hydronium ion, and chloride ion, okay? Now weak electrolytes. These dissociate, but only slightly. More than 90% of the molecules are still intact. Once you put them in water, they're still intact 90% of the time. The most common examples of weak electrolytes are the weak acids and weak bases, and we'll learn more about the weak acids and weak bases in a subsequent unit. But finally, the non-electrolytes. These are molecular compounds, covalently bonded compounds, in other words, which dissolve but show no tendency to form ions. Okay, so sugars such as glucose, sucrose, and organic molecules called alcohols are non-electrolytes. So if you have, for example, sugar and you dissolve it in water, it will dissolve, but it will not dissociate. Okay, it will dissolve, but it won't dissociate. So it's a non-electrolyte. I want to talk now about a concept called like dissolves like. What do we mean by that? Well, it's a very important concept in solutions. And here's what it means essentially. That polar molecules will be dissolved in polar molecules. And nonpolar molecules will not be dissolved in nonpolar molecules will be dissolved in nonpolar molecules. Okay? But polar will not dissolve nonpolar and vice versa. All right? So in order for something to dissolve, it has to be like the other thing. So polar molecules include, for example, H2O and CH3Cl. So you can dissolve CH3Cl in H2O. But nonpolar molecules are things like benzene, CH4, that's methane, CBr4, and CO2. So these things are not going to dissolve in these things. They will dissolve in each other, right? They will dissolve in each other. So if I have methane, for example, and I have carbon dioxide, the carbon dioxide will dissolve in the methane, right? Likewise, the CH3Cl will dissolve in the water, but the CO2 does not readily dissolve in the H2O, okay? All right, so that's that. Like dissolves like. All right, and let's take a look at an example. Which of the following is expected to be the most soluble in hexane? Now, I should tell you that hexane, C6H6, is a nonpolar molecule. It's an organic nonpolar molecule, all right? And what we want to know is which of these is going to be nonpolar. Because if it's polar, it's not going to dissolve. Or certainly if it's ionic, it's not going to dissolve. Well, let's take a look at the KCl. Nope, ionic, right? C2H5OH, well, it's certainly not symmetrical, so that would be polar, right? So the first one would be ionic, and this would be polar, so that's not it. How about, let's skip C. Let's go to D. D is H2O. You know darn well that's polar. We've been talking about that all year. And then this one, HC2H3O2. Well, it doesn't look symmetrical to me. Whatever it is, maybe I don't know what it is, but let's just say it doesn't matter. It's not it's polar, right? It has a one end that's different than the other end, so out. But let's take a look at the C6H6. C6H6 is nonpolar, just like C6H4 is nonpolar. C6H6 is symmetrical. So choice C is nonpolar, and benzene should be soluble in C6H14. So these two are both nonpolar, so this would be my answer, okay? That would be my answer. All right, folks, I want to discuss briefly freezing point and boiling point, but I think that's best left for our next unit. And so we'll call it a session for now, and I'll see you on the next one. Thanks. Bye-bye.